So, hello everyone. Welcome to today's PLC2 webinar with the name the PoC-Library, Solving All CDC Problems with a Handful of Components. My name is Stefan Unrein. I'm your today's host. Welcome back to part 3 of our webinar series focused on the free and open source PoC-Library, today with our expert Patrick Lehman. If you missed the theory and the hands-on parts from the last 2 weeks, you can find the recording available on our website. So today, it's about PoC synchronization primitives and CDC components. But before we get started, I want to have a couple of points noted. The webinar will be 1 hour, including the Q&A part. You will find a follow-up email with the link of this recording from this session. On the GoToWebinar panel, please submit your question using the question section to the right of the presentation window. We are using a new feature which is called Slido. After the slide, you will see a QR code. Please scan it and access to a question platform. There is no registration required for that. Here you can ask questions anonymously, see all questions from the other attendees, and you can vote for the questions that you like, and this will help us for highlight the most important topics for you. Important, we will do our best to answer all the questions live. For more detailed answers, if the time runs out, we will try to follow up with you via email. You can also find here inside GoToWebinar the handout section. Here you will see the training calendar from 2025 and 2026. If you experience any technical issue, please let us know and we'll try to solve it. Now it's my pleasure to introduce today's presenter. He was also the speaker in the first part of our webinar series, Patrick Lehman. He is the head of system engineering and a long-time trainer at PLC2, but also engaged in standards development within the IEEE with VHDL analysis and standardization group, and actively contributor to the VHDL project. Patrick is also a developer and maintainer of the PoC-Library, which brings us to our current webinar series. Thank you, Patrick, for being here today. And the stage is yours.
Yeah, thank you, Stefan, for the introduction and taking over from Anna. She's unfortunately ill today. She would be usually our host. I want to highlight here our Slido app again. So there's also a ID number you can use. So if the QR code is not working for you, you can go to slido.com and enter the number 1469221, and you can then enter your questions and order them based on your votes, what we should answer first. I will keep the slide for a minute so that everyone has a chance to log in or to use this code. And as Stefan mentioned, there's no registration needed. Then we go on. For you who is maybe new to this webinar series, this is now part 3. I want to give a quick introduction into PLC2. We are a training company, or our origin is from training. So we do training and coaching. We are an authorized training provider for AMD, formerly called Xilinx. We are also a coaching provider. So in case you have questions, you need help, we can offer official trainings from AMD with official slides when it comes to all techniques around the MP-SOCs, FPGAs, RF-SOCs, and so on. Also Versals and the AI engines inside. If this is not enough to take a standard training, we can also have coaching and consultancy work in critical phases of your project. We can help you short term, And if you think you need more help, we are also offering development services. We are an embedded partner with AMD, a premier partner to offer development services. And of course, a company like ours has also some products that we are selling. This is just a rough overview over the company, but let's start with the topic itself to get technical about the PoC-Library and part 3, solving CDC problems with just a handful of components. For those who have already listened to our first 2 parts or maybe have seen us at FPGA Conference, I want to highlight again the PoC-Library itself has been forked from an older repository on GitHub to a new place. So the source code is at github.com/vhdl/PoC, and the documentation is available at vhdl.github.io/PoC. In case you have added some stars to highlight the PoC-Library or to keep this in your bookmarks at GitHub, please add stars if you like to add some. At the new place, I looked into some of our statistics and I still see that the old location of PoC-Library is still growing. So in case you wanted to give the stars to the new one, please have a look at the correct location. We would be happy to see more stars. You can also use the bell symbol for notifications. So there's an option with GitHub to get emails when there are new releases. So when we take a new version and create release notes, you get a notification email directly by the system if a new master branch version is tagged. There have been also questions in the past how PoC is comparing with other libraries. So in here, I also draw how OpenLogic is doing. We are not a competitor with them. We try to work together with OpenLogic to find non-overlapping fields of IP cores. And let's hope that the renewed PoC with version 2, version 2.1 and ongoing versions can be as successful when it comes to some statistics as the old one. Okay, let's dive into our topic now. I want to talk about multiple clock domains, metastability, and then the main part is about synchronizer variants. How many different synchronizers do exist and how many do we need? And of course, we will also talk about constraining them with XTC timing constraints. So modern designs will have multiple clock domains, that's for sure. So let's take an example here. In my example, I have an input path with some RX physical layer, some RX protocol layer, which is then converting the specific protocol to axis stream. For example, we have a certain multiplexing network, and then we have also a TX path, again converting from common protocols like axis stream to the specific TX protocols, and there's a physical layer and data goes out again. And we have here with a demultiplexer a way to switch our data streams internally with a line buffer. We can go to a DMA and bring our recorded data or our measured data into some kind of DDR4 memory. Everything in here is controlled by an AXI4 Lite configuration network, which is a tree of network components in AXI Lite. When we look at the clocking, we might find that there's an RX input clock domain, let's say 156.25 megahertz. Similar, there's a TX clock domain, but both of them might be unrelated to each other, same frequency, but not the same phase or same drift. We might have a processing with a slightly higher frequency, let's say 200, because we like even numbers. The memory interface might be even faster with 300 megahertz. And for the configuration, people usually take 100 megahertz as a good number for routing and distributing the configuration information inside of the FPGA or MPSoC design. So we see we have multiple clock domains, and now we need to talk about certain points where we cross from one clock domain to another, how we can solve here our clocking problems. First one is to get certain knowledge about your clock domains and how they are constrained with each other. So in Vivado, for example, you can go to report timing, report clock interaction. Then it's calculating a clock interaction report, and depending on the number of clocks, you might get such a big diagram in here. it's showing a cross of all input clocks or source clocks to all destination clocks and how they are constrained with each other. Usually a clock is constrained with itself, so everything on the diagonal is green. That's already auto constrained. That's an interclock path. And then we have blue and cyan colored items in here. They are constrained with data passes or false passes and so on. And then we have certain items in orange and red that are not constrained correctly. So this is what we need to solve. So in a good design, you have no orange or red colored entries in here. Otherwise, it's a design fault. So in case you would hire me as a consultant checking your timing constraints, I will look into this. And if I see orange or red, you're failing. Okay, so let's understand some basics in the background. So what is metastability and what's going on here? So usually we have flip-flops and there's a defined setup and hold time. And this is our safety boundary around the rising or falling edge of a clock when a flip-flop is working to protect the input of a flip-flop for metastability. So when you're not violating setup and hold times, everything is okay. And tools like Vivado have the static timing analysis called STA, which is taking care of this, computing your delays inside and checking if signal changes are done before the setup time is violated. This is all done automatically for related clocks, but we can't ensure this for unrelated clocks. So in case you have unrelated clocks or you have completely asynchronous input data, can be also outside from the FPGA, then your flip-flop that's capturing the input might capture the data when the input signal is roughly around half of the voltage of the flip-flop, and this might cause that the output of the flip-flop also goes to half of the operation voltage. So now you have not a clear 0 or 1 inside of your digital system, and another flip-flop, let's say in a state machine, might be influenced by that and might take wrong decisions or wrong transitions inside of a state machine. Can be also counter, whatever you have. A flip-flop itself needs a certain metastability settle time. So when we go into the state, we have unfortunately reached the state. The flip-flop needs a certain time to decide if it wants to go to a high or to a low state, and this is what we call the settle time. We can put this all together. You find this also in books and I think also in university lectures. What is the MTBF, the mean time between failure? That's the rate, how often you can reach the state or where it's a certain probability. And the key takeaways from here is one of the main contributors are the clock frequency. How often do you capture the input data? And the second one is how often do you change the input data? So if you have a stable input, no one cares for it. It's always 1, nothing can happen. So the more often you change the data and the more often you try to capture it, so higher frequencies, the worse it might get. Taking this now into a diagram. So if you use an oscilloscope and you try to measure it, you might find graphs like this. So this is like drawing multiple data changes or output changes over time. And we see here that we go into this intermediate state at half the voltage, and with certain probabilities, we are changing either to 0 or to 1. Unfortunately, I cannot find any good measurements of nowadays technologies. These images are from the internet and a little bit older. So it's quite hard to find up-to-date data on it and how current technology would behave. Yes, so how can we now try to solve this? The common approach is a 2 flip-flop synchronizer, or to be more generic, an n flip-flop synchronizer. So we have at least 2 flip-flops that try to resolve our problem. So coming from some computation, we need to have one output flip-flop in the old clock domain, and in the new clock domain, there's a first flip-flop that might get metastable. That's what we see here, DS. That's a potentially metastable output, and then we have a second flip-flop that's capturing with the next rising edge, and in between our assumption is that the metastability settle time is smaller than our clock period. From this diagram, we can also guess what's happening when you increase your clock frequency. So it might be that this flip-flop needs longer, or there's a certain possibility that it takes sometimes longer to resolve. So the higher your frequency is and the smaller your technology gets, the more flip-flops you need. So I had an unofficial discussion with AMD guys, and they said, and also with Microsemi guys, that they recommend nowadays 3 flip-flops for current technology. It's also important to have no combinational logic before the first flip-flop, so no logic in between here, except for a pure copper wire from one flip-flop to another. Otherwise, this logic in between might reduce your time you have for settling. So it's similar to increasing frequency. So please do not have any logic in between, that you have the full path length here as a settle time. What we need to discuss now is how do we disable timing checks? Otherwise, our static timing analysis might complain about unresolvable setup and hold times. We have 2 options. One is a set false path. That's the commonly used one. The better one would be set max delay minus data path only. This one especially is needed when you have higher frequencies and bigger FPGA parts that you're using. Just imagine you have 300 megahertz and a big ZU19 FPGA with like 3 to 4 centimeter die size. These are multiple clock cycles you can have from one edge to another. So you want to constrain the placer and the router in your FPGA to not take this path too relaxed. So we need to tell him with set max delay that it has maybe 1 or 2 clock cycles time, but not infinite time, which we would set with set false path. Then it could be any time in between. Okay, so these are the basics. Now let's talk about the different synchronizers that you can build or that someone can build in digital systems. For classification, I want to introduce 2 axes for classification. One is the signal form. So we have short impulse signals which are active for 1 clock cycle. That's what we call a strobe. And we have long time stable signals that are n clock cycles active. That's what we call a flag. Besides these 2 categories of signal forms, we also have continuous data. This would be if you have multiple pulses in a row, but there's not a certain distance between the pulse, so they are coming too often in a row. Then we talk about continuous data. Similar, it would be with measurement data from ADCs or so, that's continuous data. And then we have some special forms like asynchronous resets. The second category we can take is the number of bits. Either we want to synchronize a single individual bit, or we have multiple bits that we need to synchronize simultaneously from one clock domain to another. So let's put it all together into a table. Now we can say either I have 1 bit and a flag, then we need sync bits from PoC-Library. That's the classical 2 flip-flop synchronizer. Or we have 1 bit, which is a strobe, then we would take the sync strobe synchronizer. If you have a flag, so a long-term stable input, which is n bits wide, we can take the sync vector. And in case you want to have a strobe behavior with n bits, this would be, for example, you have an AXI light configuration register with a command, and you need to transfer this to another clock domain. We have our sync command. I will talk about this later in more details. Whenever you have continuous data, just let me highlight these 4. If you have continuous data, independent of the number of bits, even if it's just a single bit, you need to use a CDC FIFO. And in names of PoC, it's a FIFO_IC_GOT. IC stands for independent clock. And then for special cases, we have, for example, the asynchronous reset synchronizer. This would be sync reset. Okay, let's have a look into the implementation details of the 2 flip-flop synchronizer. PoC has a generic implementation that is working on any platform. It's generic VHDL code. And inside we have 1 metastable flip-flop followed by n-1 potentially stable flip-flop, depending on how many flip-flops you want to spend on such a synchronizer stage. As it's easy for us to implement this for n bits, we made it generic that it's internally unrolling with a for generate loop multiple of these synchronizers. Each bit is individually, so it's individual bits that get synchronized, and this is easier for instantiation and for the user. So if you have a button 1 and a slide switch and a reset button, you can instantiate this with 3 inputs and each one is individually synchronized. The hardware effort is per input bit, we need 2 flip-flops, and this is also a little bit depending on the further configuration. I will come to this on the next slide. When PoC is detecting that your FPGA underneath is an Altera FPGA, we switch the implementation to an Altera specific one. The VHDL code itself is still generic, but we are then applying Altera specific attributes. One is a preserve attribute that is not inferring some kind of shift registers, which have not so good probability for settling metastability. And another one is the Altera attribute, which allows us to apply timing constraints from within VHDL code. I will show this on our last slide. And then we also have a Xilinx or AMD specific implementation. This one is directly instantiating FD primitives from unisim.d components, and we are applying the async-rec property or attribute to the flip-flops. When we have a look at our interface description of the entity sync bits, as you can see here, you don't need to care for any vendor underneath. So internally it's switching, you don't need to care for it. You just specify how many individual bits you want to have synchronized. You can set up an init value. With syncdef, you can override how many flip-flops you want to have in your synchronizer chain. You can switch between false pass timing constraint or set max delay timing constraint. And in case you have a high fan-out signal, you can add another output register if needed. And then synthesizers like Vivado can duplicate the output flip-flop in your code and relax timing problems. For ports, we have the destination clock domain, an input and an output of bits, many bits. Now you might ask, what is this misc syncdef data type in here? This is a subtype of an integer with a range 2 to 16. So by taking tick low, we are always applying 2 synchronizer stages. The user cannot specify anything that's below 2, only above. I think it makes no sense to go beyond 16. So that's why there's an upper limit. And in case you want to change all your synchronizers in the whole design at once, you go into the package and you change the lower bound here of our misc syncdef data type to 3 or 4, and all flip-flop or all synchronizers will get more flip-flops in their synchronizer chains. In case the user has overwritten in an instantiation, this, let's say with 3, and you set the value here to 4, the synthesis will complain because it's not inside of the range of the subtype, and you can figure out at synthesis time where someone is specifying by hand a value that's too low. So it's also error detecting where you have smaller implementations or shorter implementations. Internally, the code looks roughly like this. We have a generate statement, unrolling bits many iteration. We have a data sync bit. We have a data meta, that's the output of the first flip-flop that's potentially meta stable. And then we have n many sync bits in here. So there's a single flip-flop and then there's a shift register chain. It's described here as shift register, but as I said, for certain vendors, we are deactivating the inference of shift registers for Xilinx and Altera. So they are using always individual flip-flops that have better properties on metastability settle time. And then the highest bit is used to assign it to output I. That's all the magic of a generic implementation. Okay, let's come to the next synchronizer. So the first one, the 2 flip-flop, was about flag signals. Now let's talk about strobe signals, how we can transmit a 1 one clock cycle active strobe signal to the destination clock domain. And one of the big requirements here is in the destination clock domain, we want to keep the property of a strobe. So it's also just one clock cycle active in the destination clock domain, and afterward it goes back to, let's say, for example, 0. So what we can see in here, we are using in the internal part a D flip-flop together with an XOR. This is what we call a toggle flip-flop. We use a toggle flip-flop to convert any strobe to a flag signal. So now the signal form is a flag. We know for flags that can be synchronized with a 2 flip-flop synchronizer. So we are instantiating here sync bits, which comes in also with matching timing constraints. We are in the destination clock domain now, in the green clock domain, and we can use a delay flip-flop together with an XOR to reconstruct our signal. So this is giving us, every time when both bits are not matching with each other, a one cycle active strobe output. So signal transformation from strobe to flag, carrying over to the destination clock domain, using a delay flip-flop and a XOR gate to reconstruct from flag back to strobe. This is the internal core of the strobe synchronizer. This synchronizer, as it's drawn here and as it's implemented, is independent of the source clock to destination clock ratio. In the internet and books, you find lots of implementation proposals. Sorry, 1 second. Yeah, if it goes from a faster clock domain to a slower clock domain, or from a slower clock domain to a faster clock domain, you find all weird implementations. With what I'm showing here, this is independent of any ratio from slow to fast, whatever you have. This also means the user doesn't need to care about frequency ratios to each other, and you can also modify your code later. If your systems engineer is deciding, hey, let's increase the destination clock frequency to 4 times the clock frequency, now your code might break if you have a specific implementation. This implementation here doesn't care if you adjust clock frequencies on input and output side. In case the input is not a clean strobe signal, we have some kind of protection in here. So we have a rising edge protection or detection, which is a D flip-flop with an inverter and an AND gate. So we are converting long-time stable signals with rising edges to strobes, which can then be carried over to the output side. Another part in here is a blocking of further inputs. This is done by taking the output of our signal transformation here, and after synchronizing it, so synchronizing the output here back to the source clock domain, comparing it with an XOR, and this gives us a possibility to compute if our synchronizer is currently busy, so transferring 1 bit, 1 strobe from input to output. As long as it's busy, we can block further strobes on the input side. The use case here is if you have a big ratio difference from input to output clock domain, you could send 2 strobes in here, which are inverting the toggle flip-flop too fast before the output has seen any modification, and then your data, your information is lost to the output side. So we can block the input, and this busy bit is also part of our port map, so we can indicate this, let's say, to a state machine, and the state machine knows when it can send a new strobe to the other clock domain, or in case it's busy, you know you would have potential data loss because you drive the input too fast. And this is also then the indication if you have such a situation, you're driving too many strobes too fast into such a synchronizer, then it's the case where we talk about continuous data, and you would need to switch to a FIFO for just 1 bit. Yeah, and as I said, we have an indication of busy if there are transfers ongoing. Let's have a look at our interface. So we instantiate sync strobe. We can specify n individual bits that get synchronized from one clock domain to another. We call them here clock 1 and clock 2. You can specify if you want to have the input gated. If you deactivate this generic, it saves a few hardware resources. Similar we can specify the number of synchronizer stages. This is just handed forward to the sync bits instance inside. And we see here n individual input bits, n individual output bits, and for each one, of course, the busy bits. Okay, so this was all about single bits synchronizing from one clock domain to another. Let's talk about multiple bits. Here we have the vector synchronizer called sync vector. So it's about synchronizing one data word consistently to the other clock domain. And this means we have a transfer of n bits as an atomic operation. The behavior is as follows. When the input vector is changing, so there's a detection of change inside, we latch the input data and protect it from further changes. So this group of input flip-flops is locked to not accept further inputs. We transfer a strobe to the destination clock domain as a trigger. So we have a similar implementation as our sync strobe in here for the handshake between both clock domains. And the trigger is used on the destination clock domain to activate the clock enable on the flip-flop. So now we are capturing the long time stable bits from here to here. So it's copied over to the destination clock domain. We can send our trigger back with a backwards part. So that's equivalent to the busy bit to the source clock domain, which is allowing further input changes on the input flip-flop. So it's reactivated or re-enabled that we can take further changes. And this whole circuitry is again indicating busy bits or busy state if there are transfers ongoing. So a state machine that might be connected as a writer to the input side knows when it's ready to accept further data. Looking at our interface description, it's quite similar. So we have sync vector, we have our sync def as before, we have clock 1 and clock 2, we have the input and the output, the busy indication. Because it's internally computed, we can also provide a changed output. So if the data has changed, so if there's another state machine afterwards, it doesn't need to compute or look at the bits of output. If there's a change, we can directly indicate this. This is also synchronous to the output bits. In case you don't want to drive or let it infer automatically if there was a change on the input, maybe your state machine knows it already that the input will change on the next clock cycle, we can offer here a strobe input, which is by default off, so doesn't do anything. But in case you set master bits to 0, then the strobe is taken as an indication that the input has changed. So now I need to explain what are these master and slave bits. By default, all input bits are used in a comparator to compare for changes. If you want to limit this, you can set, let's say you have an 8-bit data word, the master bits to just 2 bits, where the synchronizer needs to have a look if there was a change, and the other ones, the slave bits, are used for transferring data from source domain to destination domain, but they're not used in the comparator. So you can save comparator bits, and as it's written here, if you set master bits to 0, then there's no internal comparator, and you can use an existing strobe signal from, let's say, a previous state machine or some other indications. To fill up our table of 4 combinations, we have now the last one as a command synchronizer, which is a combination of the sync vector and sync strobe behavior. So this is transferring a single data word to the destination clock domain, and afterwards it's clearing to an idle word. So we can specify an idle word on the output, could be, for example, all zeros. And if you have an input that has changed, it's transferring this to the output, and afterwards it gets back to idle. So the use case here is for multi-bit commands, can be, let's say, from AXI-Lite configuration register or command register, or you have an enum you need to transmit from one clock domain to another. Then you would convert the enum to a standard logic vector, convert it to the other clock domain, and then you can create an enum again if needed. So interface is quite similar to the previous one, just the behavior is changed by clearing after one active cycle on the output domain to this init word. Okay, So these were the combinations of 1 bit versus n bits and strobe versus flag. I also want to show here how is the interface, or how does it look like for the interface of our CDC FIFO. As I said, it's called FIFO EC GOT. I see like independent clock. We can specify the number of data bits. We can specify a minimum depth of our FIFO. We can specify how many empty state bits we want to have and how many full state bits we want to have. And then it takes a write side clock, a reset for the writing side, a put signal. Some other implementations call this enable data in, and a full indication. And on the writer side, you have an empty vector that is indicating how empty the FIFO is. That's a guarantee how many bits you can, or how many words you can still write into the FIFO. It's not an absolute indication depending on the number of bits. Let's say you take 2 bits, you can specify here, or you get an answer from the FIFO if it's filled by 1/4, half, or 3/4, or if it's completely full with a full bit indication. On the read side, of course, we have a read clock, a read reset. We have a GOT signal that the next component after the FIFO has consumed data. We have a valid bit and data out. And here we have a fill state indication. So again, assuming 2 bits for F state RD bits, it would mean if there is a fill rate at least of 1/4, half, or 3/4 of your FIFO. And in case valid is 0, it means it's empty. That's the interface of our FIFO. Okay, so this is from implementation side, and I want to spend my last minutes now on talking about timing constraints for synchronizers. The first idea is to use relative timing constraints. So we are writing timing constraints per VHDL component, not any global timing constraints. These are then independent of number of instances, independent of your hierarchy in your design, and independent of code changes. So if you move your synchronizer or a whole IP core to a different location, you don't need to rename or move your timing constraints because we are relative to the VHDL component. It also reduces the number of timing exceptions that you need to write into a global XDC file. In an ideal world, you just have your input clocks, you have these relative timing constraints, and there's no further timing constraint needed in your design. It also simplifies checking the clock interaction report that I showed before, this diagram with one clock against another clock. The idea here is if you have a VHDL component with a relative timing constraint, then it will be automatically constrained and it's popping up in blue or cyan color. If you missed to integrate a synchronizer from the PoC-Library, it will be red. And in case you want to test these relative timing constraints, there's a tickle command called current instance that has a similar behavior. So you can move your focus or your context into the design hierarchy and test such relative timing constraints. So let's take our sync vector as an example. As I said before, the 2 flip-flop synchronizer is already constrained in my assumption with the timing constraints for sync bits, either with set false pass or set max delay. So this part is all done. And the question is now about the data pass here, what we can do. And the basic idea now for my approach is, can we figure out what is the driving clock that's used for input clock domain and output clock domain? Can we figure out what clocks are driving the flip-flops? And if we get them, can we compute the relation of clocks automatically? And therefore, the PoC-Library has this timing constraint, set max delay. So we set a maximum pass delay between A and B from get cells D0 rec and some regular expression. So this get cells is finding all input source data flip-flops called D0 in our code. So we constrain from here to all flip-flops D4 on the output clock domain or destination clock domain. data path only, so just the data path between input and output. And now let's read this constraint further from the end of the constraint. So with get pins D0 reg 0 C, I'm accessing the input side flip-flop bit 0. This will always exist because we have usually vectors starting with 0, and the clock pin of this flip-flop. If I have the pin, I can use get clocks of object for this pin. So I can ask this pin, what is the driving clock of the C pin? And if I have the clock object inside of Vivado, I can use get property period to read out the period of this clock. So here I might get 10 nanoseconds if there's a 100 megahertz clock driving the C input. Similar, I'm reading out what is the period of the C pin, of the clock driving the C pin on the destination clock domain. That's what we get here in the second part. And now both periods, let's say 10 nanoseconds and 5 nanoseconds, are compared with each other with a minimum function. And this is then computing the minimum between 5 and 10, which gives us 5. And now we are constraining this data path here to 5 nanoseconds. That's all the magic. And in the documentation, it's also saying apply the scope to ref property of the XDC file to sync vector. That's the name of the entity. And now Vivado takes care of applying this timing constraint file for every instance of sync vector in your design. And you cannot miss any timing anymore for these synchronizer stages. Okay, this is a technique for Vivado. Now you might ask what we can do with Altera, and they don't have, unfortunately, relative timing constraints like that in a SDC file, but there are other techniques available. I'm taking here an example from SyncBits Altera. So that's our 2 flip-flop synchronizer instance. We can use the attribute preserve to preserve bits and deactivate shift register extraction. And another one is applying Altera attribute. And in here you see with minus name SDC statement and then double quotes within double quotes, set false path to, and then some timing this or path description in here. We can have embedded SDC statements for Altera tools inside of our VHDL code. And again, here, this constraint is written in a relative way. And another constraint we are applying is a synchronizer identification forced if asynchronous. That's another attribute that's applied for the first flip-flop. So with this technique, you're also able to apply relative timing constraints for Altera tools. Taking this all back into our clock interaction report, it should look like this. We have no orange and red colors anymore. And as I said before, in case you have a red or orange path inside, it's very easy to check what happened with your design. You have only 2 choices. First choice is you forgot to add a synchronizer with relative timing constraints. Otherwise, if the synchronizer is in the design, it would automatically constrain and not be visible in here as red or orange. Or second option you have in your design, by accident, you have a typo, whatever, or design mistake, you connected a signal from clock domain 1 to clock domain 2, which should have never been connected. So one is a logical error or coding error, and another one is you forgot a synchronizer. There are no other possibilities for your timing constraints. So for our takeaway, just to put in the slide again, we have either flex or strobes, 1-bit or n-bit. That's what we can handle with 4 synchronizer variants. And for continuous data, we have a FIFO. And then for some special forms, we have the sync reset, which I did not explain in this presentation right now. You might think about, I have different implementations in my company, or I have seen different things in lectures, in books, whatever happened. Whatever you have, we can unify them to one of these 4 variants. So people try to come to me or to Stefan to show new variants of synchronizers that exist that we did not consider. And whatever we could do since 8 years now, we could prove that they are just special variants or reduced variants with less functionality than the existing ones here. I'm inviting you to propose a new one if you have one, but I doubt that we find a new variant. Okay, that's it so far from my side, presenting it, what we have done inside of PoC with synchronizers and basic elements. Here are again the code for Slido. If you want to ask questions, I would also then go to the question platform. You find our webinars on the website that are recorded. Also, this one will be available in 1 or 2 days. And I also want to highlight that we have the FPGA conference next year then in Munich again. So if you want to reserve the date, save the date, it's available in here. We also prepared 2 questions from our side in Slido. Let me go back to Slido itself so that I can see the questions. If you want to have more topics covered from the PoC-Library, where was it? Here. If you want to have covered more topics, like what different FIFO variants we have inside, or how do we do switching between vendor-specific implementations, give a like here in the questions, and we take this as a hint to prepare another webinar.
So thank you very much, Patrick, for this really interesting talk. So we have a couple of minutes left for the questions. So you are all invited to add your question to the Slido page. Here you have again the QR code. Please go to the site and add the questions. And let's go through the first questions that we get from our attendees. So the first question that we have is, does the FIFO CDC work with first word fall through?
Yes, that's the default. We have no other implementation. And I think also from design side, it makes no sense to have the older implementation. So with Xilinx FIFOs, for example, you can, or you need to select this. It's not the default for them. I don't know why they do it. So first word falls through is the best way you can have to implement it.
Okay, thank you very much. Next question: how are resets handled inside the CDC blocks?
So there were no resets at all in the CDC blocks that I showed you. So when we talk about bits, strobe, vector, and command, because they are synchronizing to the other side, they are immediately ready again. And so the data is like, feed it through, pipeline through, and 3 or 4 cycles later, they are already ready again. And if you try to implement resets on them, it's quite complicated because you have 2 clock domains that need to agree on a reset. That's usually done again with synchronizers. So you would add synchronizers to the synchronizer to synchronize the reset, and that makes sense. It's a different picture when it comes to FIFOs, so the CDC FIFO that has resets. But be careful with resetting. So if the receiving side resets, you also need to inform the sending side that you killed the data that it thinks that might be inside of the FIFO. It's quite complicated.
Thank you. So the next question, is the RTL publicly available?
The RTL, so
the code.
The code, yes. The code is on GitHub. Everything is open source. It's all on GitHub. And let me go back once. Whoop, sorry. Yeah, I have it. We have github.com/vhdl/PoC. There you have the code. And on vhdl.github.io/PoC, you have the documentation.
Good. The next question, we have 2 left. What type do you use if you, for example, want to transfer an error counter across a clock domain where the individual bits are not independent of each other?
So an error counter. If they're not independent of each other, so it's, yeah, that's a set, it's a counter, then it would be a sync vector to transfer to the other side, because then the whole integer value that's inside gets synchronized to the destination clock domain. The important part is here, how often do you want to read the error counter and how often it's incrementing. If it's just about having the latest state and you can afford 3 to 4 clock cycles for synchronizing, sync vector is okay. In case you want to see all increments in between and they're not like linear incrementing, they are hopping like +5, +10 and so on, and you want to see the intermediate states also of this error counter, then we're talking about continuous data, and then you need a FIFO. Otherwise, if it's just having a look at the latest state that was synchronized, sync vector.
Okay, thank you. And we have a last question, which is, can I switch from clock interaction report to the specific VHDL code?
Where the error is. I see. I don't think so. So it's showing what clock domain is not constrained with each other. I'm not aware that you can see what code line is generating it. We know which are the source and destination clocks. Usually what could happen is if you go to the normal timing report, so run timing analysis or timing report, you have the interclock settings or interclock drop downs, and then there's the intraclock where we have, let's say, from 100 to 200 megahertz. And if you open this one, you see where you have maybe failing timing constraints or even ones that are good. And you can have a check inside if you find timings, let's say, of 2 nanoseconds, which you don't have as a constraint and no frequency that's so high. That's an indication that there's a constraining missing. So if you have weird numbers, but it's not yet failing, that could be one. Do you have any other idea, Stefan?
Yes, there is another thing which I can add here. So if you know which clock domain it is, there is in complementary to the interaction report, clock interaction report, there is a CDC report,
this one, yeah,
which you can open up, and then it shows you each individual CDC that you have in the system. And here you can then go to the clocks that you have seen in the clock interaction report, and there you can find the exact schematic part which is creating this failure basically in the clock interaction report. So thank you much for all the questions. I think we have answered all of them.
And I see that we have 9 upvotes for FIFO variants. So we will sit together and prepare another webinar, maybe December, maybe January, let's see. Okay, thank you for the interest also in this topic, and we are happy to deliver this to you and show some more insights.
Yes, then that brings us to the end of this talk. Thank you all for joining us today. As a reminder, a link to the recording will be emailed to you today. If you have any further questions, please don't hesitate to contact us directly. Just as a reminder, the room will be remained open for a couple of minutes ongoing, that you have a chance to submit more questions that we could answer later on. And yeah, let us know what you think. A quick feedback survey will be launched right after this webinar ends. Please don't close your browser window, as your feedback is incredibly valuable to us. So this was our webinar, the PoC-Library, solving all CDC problems with a handful of components. Thank you for your time and have a great day, everyone.
So I think because we said we are open here for more questions, there popped up a nice question. It's about migrating XPM macros to PoC CDCs. I think that's a good idea that we write this into the documentation, how we could migrate from one to another.
Yes, might be a good point that we could add.